Okay, good morning. We can start this session. I am glad to be the chair of this session, Advancements in Hydrogen System Modeling, from Fundamental Principle to Complex Systems. I am happy to invite to the stage Mr. David Robinson, please. Mr. Mark Milenia, he will be present with us online. I think he's already online via Zoom. And I am also happy to invite Mr. Chris Pingles. Okay, as you see during the first day of the Power2X summit, that the hydrogen will play an important role for decarbonization of various sectors, including transportation, industry, and power generation. But also you realize that, okay, the people are half of the people are convinced about that this role that will play the hydrogen, other ones are not yet convinced. And this comes the role of modelization is a very important tool to show the roadmaps and also to show the benefits of the hydrogen that can play in decarbonization of the industry in various sectors of industry. And today I will just give you a brief or short biography of our distinguished speaker of today. We have with us Dr. Mark Milenia, is a senior advisor supporting the system analysis team within the Hydrogen and Fuel Cell Technologies Office at the United States Department of Energy. Dr. Milenia has over 20 years of experience analyzing sustainable transportation energy systems, focusing on hydrogen system technical economics, scenario development, and sustainability assessments. Before joining Boston Government Services, he works at Great Wall Motors, FTX Energy Technologies, the National Renewable Energy Laboratories, and the Institute of Transportation Services at the University of California. David, he has provided analytic support for two committees of the United States National Academies of Science and was a member of Transportation Research Board Committee on Alternative Transportation Fuel and Technologies. He has a BA degree in physics, MS in civil engineering, and PhD in natural resources and environmental from the University of Michigan. The second speaker of today is Dr. David Robinson. Has 15 years of experience in energy system modeling and is currently leading the modeling activities for energy exemplar developer of the Plexus energy market modeling softwares. He has a particular interest in whole system energy planning and has worked extensively with system operators across Europe, Middle East, and Africa in the development of national energy transition pathway and assessments of energy security. Moreover, Dr. Robinson is also actively working with asset investors to model the behavior of this disruptive technology in the market and assess potential ARP. And the last speaker is Mr. Chris Pringles. Mr. Chris Pringles on his professional journey in design desk of renewed Belgium engineering office. There he gained invaluable international experience in business development, project financing, and general management within challenging and dynamic business environment. Chris' experience extends to the solar PV, wind, and energy storage technology, as he actively contributes to numerous projects across Belgium, France, Slovenia, Poland, and the Czech Republic, Singapore, India, various countries in Africa, and the Middle East. In 2014, displaying his entrepreneurial spirit, Chris founded Tiger Power, an innovative startup focused on bringing stationary hydrogen application to off-grid and underserved markets. Recognizing the vast potential of hydrogen, he paved the way for its adoption in areas lacking access to reliable power grids. As a visionary, Chris has constantly been at the front of the green hydrogen revolution. Since 2019, Chris has been instrumental in piloting and developing gigawatt scale green hydrogen projects for diverse international consortia. His deep knowledge of various green hydrogen in conversion technologies has laid the foundation for cutting-edge feasibility studies and the implementation of concrete projects. Chris' experience track record position net zero work as a front runner in architecting large-scale green hydrogen initiatives, reflecting the company's commitment to pushing the boundaries of sustainable energy solution. After this short introduction of the speakers, in the session of today, we will try to answer too many questions. I will give the floor first to Dr. David Robinson, that he will have a short presentation where he can also show us what are the main models that exist and how we can apply them. The floor is yours.
All right, thank you, and very excited to be here today to talk about hydrogen modeling or more generally power to X modeling. And when we're talking about power to X, really what we're talking about is essentially modeling the interaction between multiple different sectors. And this has been a major focus in the work that I've been doing over the past 5 years or so, as we start to see more requirements in order to be able to assess capital cost recovery from assets across multiple different sectors and multiple different components across the energy value chain. So if we just think about the modern energy landscape in terms of the interactions that we have, so when we talk about power to hydrogen, what we're really having to consider is what's happening from the perspective of various different generation assets, so traditional generation assets, renewable generation assets. As we start to move towards more distributed generation, we're also thinking about what's happening from a transmission system perspective and from the perspective of congestion on the grid. And then we have an interaction into the actual hydrogen itself. So we're looking at how does hydrogen compete against other potential energy carriers, and how do we utilize that hydrogen for various purposes, whether that be industrial purposes, whether that be transportation, whether that be looking at actually using this as a feedstock as hydrogen is used today, and blending multiple different gases together. So the energy landscape is becoming increasingly more complex in terms of modeling. And what we've been focused on within Energy Exemplar is the development of a fully co-optimized model, which is able to look right across the energy value chain. So this is the most advanced model globally. It's being currently used by more than 500 organizations across the globe. And what I wanted to talk to you a little bit about is our experience in developing a fully co-optimized pan-European model. So what we've recently completed our work on is a representation of a model for the European network, where we have modeled every single generation asset across the region. We've also modeled every existing gas asset and all gas infrastructure, as well as modeling fully the future hydrogen sector, which is based upon the outlook of ENSOG and their 10-year network development plan. So we've basically looked at at having representation of the existing assets, the future assets, and also considering elements associated with demand side management. And the idea here is to be able to assess the various different energy transition pathways and understand the role of hydrogen in the future energy system. And if you look at the EU targets, I mean, even if I'm not focused upon the hydrogen sector, but I'm focused, for example, around power or I'm focused around gas, I mean, you can't really model anything beyond 2035 without considering hydrogen within your models, because essentially looking at the renewable targets, you end up with far too much unserved energy, dump energy inside of the system. So your options are that you either find a large amount of curtailment inside of the models, or you find a way of being able to absorb all of that renewable energy. So we've really focused around how how hydrogen will interact with the rest of the energy system. So as a starting point for the panel discussion today, what I wanted to do was share with you just some of the observations and the lessons learned that we have picked up from a modeling perspective in terms of developing this sophisticated pan-European co-optimized model. So what did we learn? The first thing that that really came to our attention is, of course, data. So data, whenever you're building a model, is a challenging component. Trying to find the right data, trying to normalize the data across multiple different data sources. This is becoming a lot more challenging when you're starting to look cross-sector. So what I've demonstrated here, this is just a couple of examples where we were looking at data which is publicly available around gas consumption within the power sector. So gas for gas turbines over the last 4 years. And we looked across multiple different data sources, which are authorities within Europe. So looking at the transmission network operator for electricity, the transmission network operator for gas. For those of you that are not familiar with the European entities, there's also the European Network of Transmission System Operators for electricity and gas. So that is essentially a body which coordinates the development of all projects at the pan-European level. And then we have the European Office for Statistics. So we looked at essentially gas for power consumption across all of these different entities. And what you can see here, if you look on the left-hand side, this is what's happening in Portugal. This is exactly the same data, but every one of these entities has a very, very different view. And here we're not talking about a 10% deviation. I mean, we're talking about 150% difference between these different data sources. So really, in terms of being able to look cross-sector, there is really a big focus in terms of the data that goes into the model, in terms of trying to establish a common baseline, and what does that data actually represent when you're talking about, for example, what's happening in the power world versus what's happening in the gas world. And this would be reasonable if we found consistency across the geographies. But to make this even more complex, what we found was, if we look, Italy is a prime example, but actually the relative difference between these organizations in terms of where the data was consistent, where the data was greater or less, is completely different in Italy to what it is in Portugal. So there's a lot of work that goes into actually developing the right data inputs for the model itself. The next challenge that you have when you start to model across multiple different sectors is looking at the fundamental differences between those sectors. And a lot of this is around the time granularity associated with when decisions are made, as well as how the markets are operating. So, for example, if you look at the power sector and you're looking at electrons, here you've got to balance, of course, supply and demand in real time. And you can ramp units up and down very, very quickly in order to respond to real-time conditions. So you're typically modeling on a very granular level of detail. So generally, if we're talking about power, you're modeling at an hourly level of resolution. So if you're looking across a year, you're considering 8,760 periods, potentially even sub-hourly levels of resolution if you're talking about analyzing the impact of renewables. It's not uncommon to see modeling down to 30-minute, 15-minute, even 5-minute level of resolution. By contrast, if we're looking at gaseous commodities, here typically you tend to have continuous production. So if I'm looking at your traditional methane or LNG based markets, you're tending to look at longer term considerations. There's not really so much ability to be able to change your production significantly within day. But this is okay because you have long duration storage and you have line packing within your networks that can take care of some of that volatility within day. And then when we move to something like hydrogen, we end up in this unusual position where actually, depending upon the type of hydrogen, we're looking at very different kind of modeling, because if you're looking at green hydrogen production via electrolysis, here you're very much looking at, for example, the time frames of the power sector, where actually you're responding directly to market conditions potentially. So you're ramping up and down your production, of course, trying to consider the impact on the longevity or the lifetime of the electrolyzer. But you also have that component of long duration storage, which typically is a challenge within the power sector. So there's a lot of consideration in terms of how do you fundamentally make these two models work together when you're looking at something like gas, which typically is operating on the sort of the gas day level, and very often a lot of these models are just focused upon modeling what is the monthly consumption, for example, versus running the electricity side of the model, where you're actually wanting to consider what's happening in that very granular hourly level of resolution. And then the other thing, which is actually until you get into the details of modeling, often not at the forefront of consideration, and that is how do you deal with different units of measure. So, for example, within the power sector, I mean, you're generally always talking about energy. You're talking about megawatts or megawatt hours, gigawatts hours. When you're talking about gas, you're often talking about volumetric based units of measure. And then you get into complexities associated with things like, low heating value and high heating value. I mean, by its very nature, the power system works on low heating values. The gas sector, by contrast, typically you're talking about high heating values. And so if you're developing a fully co-optimized model, whereby you have gas being produced and then being passed directly to, for example, a hydrogen generator, then typically all of your data on the gas side of the model is being dealt with in the low heating values, and then you have to somehow convert all of that within the model itself to high heating values as you move it into, for example, your efficiency data for your power sector. So again, a lot of challenges that we encountered as we actually went through the development of this fully co-optimized model. And then the last piece, and I'll sort of wrap up my part of the session here, is just thinking about what does the hydrogen market of tomorrow look like. So at the moment, the hydrogen sector, hydrogen is of course really a feedstock, and so the hydrogen model tomorrow, where we start to think of hydrogen as an energy carrier, looks very, very different to the markets of today. And so when we talk about the price of hydrogen, and very often a question that we get is, what's the price of hydrogen? What's the price of green ammonia in 2030 or in 2035? Well, the question is, what does that market look like in order to assess the price? Does that market resemble something like a power market, which is based upon short-run marginal costs and short-term fundamentals, or does that look something like the natural gas market, which is based upon long-run marginal costs? So it's I guess a philosophical question that I would pose to the audience to think about in terms of the outcomes of these models and how do we actually use that information in decision making. Thank you.
Okay, thank you, David, for sharing with us your experience in developing a hydrogen system modeling and also highlighting the main challenges that we are facing when we are developing this kind of system. I will ask the second speaker, Mark Millenia. You are with us online. Okay, thank you. Mark Millenia, he will stress or he will show what is the main benefits and limitation of the current hydrogen systems model. Mark, the floor is yours. Please, you come.
Great, thank you very much. Let me just check. Can you hear me okay?
Is okay, but we cannot see the slides. If you can share the presentation of Mark Millenia. Please, Mark, if you can share your slides.
Wait,
okay.
I think I can
now
do it.
Now we can see your slides, Mark. Please go ahead.
Okay, great, thank you. So I'm going to present some of the models that we use at the US Department of Energy and talk about some interesting interactions. So I think it's really nice to follow on a detailed presentation from Energy Exemplar and Dave's detailed look at that. And I'm going to cover that type of model, but then also look at a couple other types of models that I think are important for hydrogen. So if we could go to the next slide. So I'm not going to read all of this, but on the right-hand side, there are three different general types of models. So at the top are models that look at simulating markets, so more on the prices, as Dave was mentioning at the end of his talk, and also on the influence of policy. And then on the bottom right is
Sorry,
what
Mark,
I'm calling...
we cannot hear you very well. Please, if you can speak close to your microphone, please.
Oh, thank you. Is this better now?
Now it's better.
Okay, great. Thank you. So the second type of model is regional planning in the bottom right, and I would include the Energy Exemplar model in this. So detailed spatial and temporal modeling of particular regions. And then the third type of model is zooming down to the project level or the facility level, what I'm calling project assessment type models. So the diagram here is trying to emphasize what I think is important is that all of these models can inform different types of decisions. So those decisions or programs are highlighted in the gray boxes. So for example, carbon credit trading or sustainability standards can be informed by markets and project assessment. But to improve that capability, there are different types of information that can be exchanged between the different models. So those are shown in the arrows between these types. So for example, in a detailed regional model, we might get costs, but from a market model, we can also get prices compared to other types of energy that are being simulated in an overall energy market. So I'm going to give examples of each of these types, but this slide shows the general idea about trying to exchange information between these modeling categories to improve the overall modeling framework. So if we could go to the next slide, please. So for the category of markets and policy, I'm just showing two examples here. The one on the left is probably one that people are familiar with. So the International Energy Agency puts out a lot of interesting and important results from their global models and what they have as scenarios. One of these scenarios is the net zero by 2050 scenario, where they have included hydrogen market uptake compared to all the other technologies needed to reach net zero. So if people are not familiar with this, I think this is a good reference and a good example of how scenarios can be relevant for energy frameworks. For example, one of the takeaways is globally, a large fraction of electricity is projected to go to electrolysis in their net zero by 2050 scenario. And even though this is not necessarily a high total demand globally compared to some other studies, it does represent what IEA is able to do with all of their other modeling capabilities to show the role of hydrogen. So the figure in the bottom left shows which markets globally or which end-use demands that hydrogen is going to. So that's an example of a scenario. If I move over to the right-hand side of this figure, another example is what I would call a market simulation modeling. And the Stanford Energy Modeling Forum actually combines multiple types of energy markets within particular studies. So the current study for the Energy Modeling Forum that's happening is called EMF 37. And EMF 37 is combining multiple results from about 15 plus different energy models, focusing on North America to look at electrification and decarbonization. And in this particular study for EMF 37, they are including hydrogen within scope, and it's one of the focus points of the effort. So this is a very different type of model, and I would say that a lot of these models, they're including hydrogen capabilities in sort of the early stages of simulation, but it's still an interesting point of view. And then in the middle of this slide is showing an early journal article that's come out on this study for 37, and there are going to be multiple papers that come out of this effort on different topics, including a paper on hydrogen. So if we go to the next slide, please. So this is the category that Dave, I would say, just talked about in much more detail. And so I don't need to dwell on this too much, but just to recognize that this is a very important type of detailed spatial modeling to look at particular regions. So the two references that I have here for these figures are much more academic than what Dave showed before, but I think they're still interesting in terms of methodology, and they're attempting to tackle some of the challenges that Dave mentioned in his talk. So a lot of this is supply chain optimization for hydrogen systems, but they are also trying to co-optimize with electricity models. Probably not as sophisticated as Energy Exemplar, but still trying to tackle some of the same challenges that Dave mentioned. So that's the second general category of analysis. And I think that there's a lot of important information here that can be fed into the other two types, including prices, as Dave mentioned. And then the other important part is to have stakeholders in a particular region have one model that they can look at and try and agree upon as a good representation of their region. That's another valuable contribution of this type of model. We could go to the next slide, please. So if we move to a much smaller level of detail at a particular project, so this could be, for example, a particular hydrogen production facility that is generating hydrogen that gets exported to the region. There are a lot of important analysis tools to look at facility level, project level analysis. So at the US Department of Energy, our main model that we're using to do this is the GREET model, which is shown on the left side of this slide. Hopefully people are familiar with GREET. There are a few different versions of GREET. It's mostly used for the United States, but there are versions of GREET that have been developed for other countries, and it has been used internationally, including the MENA region. The main focus of GREET is to look at average representations of entire sectors, so hydrogen, biofuels, electricity for transportation. But due to recent developments in the US, we're also using GREET to analyze particular projects. So the link at the bottom on the bottom left is a YouTube video, a tutorial on how to use a version of GREET that just focuses on hydrogen facilities. So for us, that's important for a lot of our activities at Department of Energy. A very similar methodology is in the middle of the slide from IPHE. So there is a task force, the Hydrogen Production Analysis Task Force, that has published a white paper proposing a joint methodology that was developed by multiple countries within IPHE on how to do life cycle analysis at the production level. And the same task force is extending that analysis to include delivery and storage systems as well. And the goal here is to provide a methodology that will help facilitate market interactions and eventually trading of carbon credits internationally. So the GREEP model is the model that we would use in the US to feed into that international framework. And then other countries would use their own regional models, life cycle models, to support the framework being articulated by IPHE. So those facility level models are important for what I would call carbon credit as the program being supported by the analysis. On a broader level, not just looking at carbon, but looking at sustainability in general, there are other assessment tools that I think should be leveraged to support hydrogen, even though they haven't been used yet necessarily to analyze hydrogen projects. So the two examples I'm highlighting here are the Envision model, which is mostly in the US, and the BREEAM model, which has mostly been used in the European Union. And there are other similar assessment tools that have been used in different parts of the world to look at sustainability in general for infrastructure systems. So there's a lot of expertise there. There's a lot of track record of using these models to analyze particular facilities or projects. And I think it's important that the hydrogen community consider these as resources to look at the sustainability of hydrogen projects and systems. So I have one more slide. You could go to the next slide, please. This is one of our general overview slides for US Department of Energy, highlighting a lot of our different activities. So our program supports research and development activities, as well as early stage deployment and demonstration, and more recently in the last couple of years, large scale deployment on the right-hand side. For this particular audience in this session, I want to highlight two of the items along the bottom here. So one is IPHE has an early career network, which I think is really valuable for people, students who are entering the hydrogen sector and would like to network with other people internationally. So I encourage people to look up that early career network as a resource for IPHE. And then the other one on the bottom right-hand side is the Hydrogen Twin Cities program, where cities pair up in different regions of the world to collaborate on hydrogen activities. And I've put a link in the chat to that particular program from the Clean Energy Ministerial. And that is my last slide. So thank you very much for your time.
Okay, thank you, Chris. Thank you. Thank you, Mark, for providing us details about US model that you are using for hydrogen systems. And from here, we see the first model that was developed in Europe, the other one in USA, and the looks like are very complex systems, but sometimes we are using some kind of simplified systems. And from here will come my third question about what are the implications of simplified or complex models for drawing conclusion. And I will address this question to Mr. Chris Pringles. Please, if you can give some highlights.
Yeah. Thank you, Professor. First of all, I apologize, I don't have a presentation, but I think it leaves us a bit of time. Yeah, let's kind of an echo. So no presentation. Perhaps it leaves us a bit of time to discuss. First of all, let me share, I'm very concerned because I mean, I've been in industry for about 10 years now. So 2019, and then 20, etc. And since then, we have always been talking about 2030 scenarios, a lot of simulations, a lot of reports, a lot of strategy papers, etc. The reality on the ground that is not too much is happening. One of the things I believe is that there's a big difference between planning, with all respect, planning on national level, on the European level, on a global level, And I think for sure there's a role for hydrogen. The question is, how do we get those projects on the ground? There's very little happening on the ground today because it's very complex. And we see that there's, well, the main concern that we have is that you see papers presenting projects or potential projects at prices which are very far off from reality with fairly simplified models. I'll give you one example. There was recently a report on renewable ammonia production in Oman that was contemplating a cost of about $430 by 2030, which is about 6 years from now. If you start developing, if you would have your land rights today, you would be lucky to get your plant operational by 2030. If we compare those simulations or those reports with what you do or what you get if you do project simulation or detailed simulation on project level, the cost is at least double. I think there we need to be careful as a group of enthusiasts that we don't shoot in our own foot at the end, because policymakers, and that's what I think Mark showed, they need to have a loop, we need to create this, we need to close the loop where we go from planning level to regional level to project level and feed it back into the top level. If not, we may have a very big difference and people, policymakers, decision makers will get confused. Investors will get confused. You present the project to your board will have read reports and they will say, are you really sure you know what you're talking about? Because you present the project double the cost than what I've seen in some reports, but by renowned consultants and global institutes. So where we come in as Net Zero Works, we come in on the project level. We are a project developer, and we have developed a tool, a simulation tool that actually came as a necessity. We never had a plan to market the tool as a product, but when we were developing those projects over the last 10 years, so to say, gradually scaling up from very small applications to now large-scale projects, we saw the necessity, we had an urgent need to have a model which integrates the entire value chain. There's very good models, commercial models for wind analysis, for solar. I mean, you would have your technology licenses on the downstream part. Think about ammonia, very specialized. In their part of the job, you would have the electrolyzers to come in. I think the main challenge is to bring all those systems together and have a model that really optimizes the entire value chain, because it's an iterative process. You cannot start from the front end with renewables and then work your way through to the back. The better way is to start from the flexibility or the constraint that you have on the downstream part and make your way up to the front. If you start, of course, if you start with solar at $20 a megawatt hour, and you need about 47, 48 kilowatt hours per kilogram of hydrogen, and you add a bit of capex and opex and WACC, etc., you would come to a cost of less than $1.5 for hydrogen. The question is, or the reality is, there where you have $20 per megawatt hour of solar, you won't have a consumer. There where you have the consumer base, you won't find solar at 20 euros. You would have an electrolyzer that runs, give and take, 2,000 hours a year. And then you need to have a direct application. If you're lucky enough that you can feed your hydrogen into an existing network, which is kind of stabilized by a grid operator, of course you would do. If you can feed it into an existing ammonia loop, that's fine too. If you would kind of have direct use or across the fence use, there's potential there as well. Now, if you talk about Morocco, if you talk about export projects there, sometimes it goes wrong because in Oman, of course, in Egypt, very good wind, very good solar, but you will need to convert to a carrier, whether it's liquefied hydrogen, difficult. It's a complex process that needs to run, or that is designed to run 24/7. So you need to, ammonia loop for the same thing. You need to integrate storage, you need to integrate compression, you have to optimize your energy mix, etc., etc. That's where I think an overall model, which we are using on a day-to-day basis, really brings a bit of reality in the game, and we have to see as a community how we can feed back those results back into the planning models. So, I mean, generally speaking, or to summarize, I think there's a need, of course, for planning models. There's a need for really detailed and fairly advanced projects or models on a project level, and we have to make sure that we feed back into the loop so that policymakers really understand how a concrete project, which is to be delivered in 2013, fits into the overall scheme.
Okay, thank you, Chris. That's okay. That means even that if we try to simplify our models, at the end of the day, we find ourselves with a very complex model. Yes. Okay, I have other question for David and Mark, both of you, about, because when we are developing models, the first thing coming to our mind, how we can trust our model, how we can validate them. Taking in consideration that we have now access to few data related with this field of hydrogen, ammonia, how we can validate these models, and also if there are some works now worldwide to have a cross-checking of the models to validate them.
Yeah, I think this microphone is a little better. Yeah, so it's a great question. I think what you need to do is you need to break this down into established technologies and emerging technologies. So the approach that we are taking in terms of validating the models themselves. So we first of all look at the established technologies and we benchmark that against historical behavior. So essentially, if we're looking at a regional model or a market-based model, like we talked about, what we would do is we would look and we would see, is our model providing the correct response to current market conditions by benchmarking against things like what are market prices looking like, what are the mix in the current market, and ensure that we have a reasonable degree of alignment in terms of what those market dynamics look like. What we then do for the emerging technologies is we essentially benchmark the operation of those technologies against projects which are up and running today. So actually, I mean, for clarity, with the model that we have within Energy Exemplar, which is a model called Plexos, we also, a large proportion of our customer base are doing project-based modeling as well.